Hello everybody, this is Luboš Pirkl from CFD Support. I am here in our Prague office with my colleague Radek Máca. Hello Radek.
Hello Luboš, and hello to all attendees.
Yes, so how are you today, Radek?
Yeah, I'm very fine. I am looking forward to this webinar.
Okay, perfect. And together with us on the other line there is Oliver Felde from CFturbo in Dresden. Hello Oliver.
Hello Luboš, here's Oliver speaking.
Okay, hi, so the same question, how are you today? Are you ready?
I am ready and I'm fine, and I'm also looking forward to have this presentation together with you.
Okay, perfect. So it seems we all are ready. So hello again everybody. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design a centrifugal pump from scratch in CFturbo, and then how to simulate it and evaluate it in turbomachinery CFD. The webinar is being recorded, and its recording will be made available on our YouTube channel. And yeah, I think we can start. I hope everything works well. In case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. So please let me start with who we are and introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support. I'm here with my colleague Radek Máca. Radek is our head engineer and senior developer here at CFD Support. And finally, in Dresden, there is Oliver Felde. Oliver is Senior Manager CAE at CFturbo. He is responsible for consultancy and software development, especially for the implementation of turbomachinery design theory and related algorithms in CFturbo. About the program, the webinar is going to take about 1 hour, depending on the number of your questions and comments. There will be 4 parts in this webinar. In the first part, there will be basically this general introduction. In the second part, there will be live example. Let's call it the design part or CFturbo part, where Oliver is going to introduce CFturbo a little bit, and he will show a live example of centrifugal pump design from scratch in CFturbo with final export of the designed model to turbomachinery CFD. In the next part, there will be another live example. Let's call it the simulation part or turbomachinery CFD part, where Radek is going to show the turbomachinery CFD simulation and evaluation of that centrifugal pump, which was beforehand exported by Oliver from CFturbo in the previous section. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to put your questions. There is a special window where you can put your questions, and you can also send us an email to info@cfdsupport.com, and we will gladly answer all your questions later in this webinar. Feel free to put your questions. It's important part. We believe we can tell you everything we know, and it's your time. So take your chance. Yeah, so let's start with the design part of the webinar. So I'm gonna hand over the presentation to Oliver. So Oliver, will you tell us about CFturbo?
Yes, I will. Thank you, Luboš. Well, CFturbo is a German-based company that produces the design package CFturbo, which is a modern, powerful, and user-friendly software tool for the conceptual turbomachinery design. And the name conceptual is included into this presentation because we do not start from points and connect these points, but from the latest design theory on turbomachinery. Right now we have 200 active clients globally, and CFturbo is divided, or the package is divided into different modules, and that can be used to design pumps, fans, blowers, compressors and turbines, and of course stators that can be vaned or vaneless, plus diffusers and volutes. And all these modules also can be used for both radial and actual machines, or to the design of that. We serve the following industries. Amongst them are aerospace, automotive, consumer products, and so on. And also semiconductor industries, because very often in computers you find special fans to, for instance, cool the CPU, and that's why it's also used in that branch. Okay, thank you, Luboš.
Yes.
I'm going to now share my monitor with you out there, and I hope you can see now the
Yes, we can. Yes, we can. It's perfect.
Okay, and that gives me the chance to start with a live example. Today I'm going to design a pump. That's why I choose from that list the machine time pump. The very first thing one has to define is the setting of the design point. And here you see now clearly why it's called a conceptual design package, because you design a machine especially for a certain operating or design point. For that type of pump, the design point consists of a flow rate that could be, for instance, 450 cubic meter per hour. It should produce a certain head of, for instance, 30 meters, and should run on a speed of 1,770 RPMs. We also need to know about the fluid that has to be conveyed, and that's going to be water, for instance, in this example. And with all these definitions and informations, we can directly calculate some informational values, like, for instance, the specific speed, which is very useful in the design process, which you will see further on. Once I press OK, I'm prompted to add a new component to the project, and I'm going to start with the impeller, and that's why I choose radial mixed flow impeller from this list. And the very first design step is what we call the main dimensions, and in that main dimension, the inlet diameter, the impeller's diameter, and the outlet width has to be defined. And that can be done in both ways. You can directly type in diameters, for instance, that you have in mind, or you can let CFturbo make proposals to this end. And for the proposals, some empirical parameters are used, which again come from the design theory, plus some balance equations which are solved in one dimension. So for instance, if you look at that second parameter, it's the work coefficient, and this again is, or its value is proposed by CFturbo, and that proposal is based on data that will be shipped with CFturbo, and those data are given in what we call the approximation functions. And here, for instance, you see a proposal of CFturbo with respect to the specific speed, which again depends on the design point. And CFturbo will propose something like 0.85 for that specific speed value. And see on the left-hand side, there are a lot of empirical parameters implemented, and you can use them, or you can also override those data with your own knowledge just by clicking add your own function and add a table of points, and then in the design process you can use that. And the data will be saved on your desktop in your company, and it will stay with you, so everything is still in your hand and no knowledge will leave your desk. Okay, again, by pressing calculate or activating the automatic mode, one gets proposals by CFturbo, but what can be done afterwards is one can override them just to get rid of the decimal places, for instance. And that's what I'm going to do here. Once I press OK, then in the meridional view, I'm going to see that meridional contour. It's not curved yet because only the diameter and the outlet width is defined. In order to get a nice shaped hub and shroud contour, the next step has to be performed where shroud and hub are presented with the help of Bezier curves. The same applies for the leading edge, and you can grab every control point at any time, and once you press OK, the complete geometry will be updated. Also, by clicking with the right button on a control point, one can set directly the parameter of a control point, like for instance that Z coordinate, and that will be taken, and again you get an updated 3D geometry. In order to tell whether how the meridional flow would look like, one can switch on these potential flow-based calculations here and would get the meridional velocity component distribution averaged with the in circumferential direction. If I press OK now, then of course the meridional view will look accordingly, but also one would get a first 3D model of the pump. The next step is to set up the blade angles at leading and trailing edge, and also to set up the number of blades. Again, for every parameter you get a proposal by CFturbo which you can change or accept. So I, for instance, increase the number of blades here. One can define a certain incidence, and more importantly, one can both either set the blade angles at the outlet or at the trailing edge, or again let CFturbo calculate it, and it's going to be calculated in accordance to the design point plus in accordance to the slip model that is implemented and is chosen again by the user. And we have implemented a lot of different slip models that can be chosen from. Of course, there's also a user-defined one here. Okay, once I press OK, nothing else has happened because it was just the angles at leading and trailing edge. A 3D representation of the blades can be reached once I have finished what we call the mean line design step. Here, the mean lines or camber lines are again represented by Bezier curves, where the tangential direction at leading and trailing edge is in accordance to the blade angles that have been defined just in the design step before. Again, there is a preview, a 3D preview that can be watched during the design process, and also there are some informational calculations that can be watched, like for instance an estimation of the relative velocity distribution on different spans. And if you change, for instance, the rep angle by just grabbing this last control point, then you get immediately an answer of how the relative velocities could look like. And if you compare it with some limits, then you can tell whether your initial design is on a good way or not. If I press OK and go back to the 3D model, what I'm going to see is an impeller with blades that have a zero thickness. Of course, the thickness is something that has to be added because it depends on the material to be used or on the manufacturing process. And to this end, there is a design step called blade profile design step, where you can either define perpendicular thickness values linearly distributed between control points, or you can have, again, freeform distributions, Bezier-like distributions like that, where you can, in that design step, round the leading edge and the trailing edge if you like. I'm going to stick to the simple one because I want to show you the next design step, which we call the blade edges. If you have not had round leading and trailing edges in this design step before, you can do that in the very last design step with respect to the impeller. And here you can set, for instance, an elliptic leading edge shape and an simple trailing edge shape, which is trimmed to the outlet. So it's probably best shown if I zoom into that frontal view here. If I take that trimmed on outlet checkbox out, then you see here the trailing edge is not trimmed anymore. And if I activate it again, then you see what is meant with that. Again, pressing OK will yield now an updated 3D model of the impeller, and this is a model I'm going to save now on my desktop. Because we want to do a CFD simulation of that pump afterwards, I'm going to add what we call a CFD setup and a certain tangential or radial extension. This is just used for the CFD simulation because very often the CFD packages don't like it if the rotor stator interface is directly connected to the trailing edge. Okay, because I want to have a spinner here in front of the impeller and not a shaft that goes through the complete stage, I'm going back to the main dimension, set the hub diameter to 0, go afterwards to the meridional contour, add some extra curves at the inlet, and by doing so I get very quickly a decent spinner. Again, change the values by right-click on it. For instance, 40 and 60. Oops, that was too much. Make the second curve to Bezier, have a tangential connection between those two Bezier pieces. Change probably a bit the location of the leading edge, and here in the right hand side you now see that we have a nice spinner. And if I press OK, because everything is parametric, we get immediately a 3D update of the complete impeller. Okay, because I want to design a complete stage, I'm going to add a volute at the outlet of the impeller. Again, the first step is the inlet definition. The second step is what is the general shape of the cross sections of the volute. I'm going to stick to the round one. Next step is to define how is the distribution of the cross-section areas with respect to the wrap angle of the volute. And to this end, there are again a couple of models implemented. So the velocity-based model takes the inlet swirl and calculates with the help of Leider's rule or Stepanov's rule that distribution. But of course, one can also switch to what we call a geometry-based design, where one has to define the final outer radius and also can give the distribution between the inlet radius or the starting radius of the spiral and the final radius. Something like that, for instance. Again, there's a 3D preview which will be updated during the design process, and also a lot of mid-span average values that will be calculated at special sections of the component. Now I get an update of the 2D meridional view, but also of the complete 3D model of the stage, like that. But it's not finished yet because we still need an outlet diffuser plus a cutwater. And if I go back to the volute, I can just tell what is, for instance, the diameter of the outlet diffuser and what is the length of it. So I'm going to have it like 80 millimeter in diameter and 300 millimeter long. And once I've done that, the final step is the generation of the fillet. And to this end, I just type in a fillet radius, press update on 3D preview, and then if I go into press OK, I have a nice volute with a nice cutwater here. Again, because I want to prepare everything for the CFD setup, I activate the CFD setup of the volute, and also because I want to have a well-defined inlet pipe, I'm going to add an actual inlet pipe with a certain length, for instance 230 millimeter. Just simplify harp and shroud contour because that doesn't have to be a Bezier spline. And once that is ready, it's going to look like this in 3D. And let me just check the time. I still have a couple of minutes, I guess. Now I could go ahead and say make a model finishing. Model finishing means always extend all the surfaces a bit in a way that they intersect with each other, and do then some 3D Boolean operations, and by doing so one gets really well-defined solids and well-defined patches that belongs to those solids. And what also can be done here is one can add fillet radii at harp and shroud, and that's what I'm going to do here as well. And this probably takes a bit of time, a couple of seconds, but it's necessary before you do an export, for instance, for further CFD simulations. And I'm going to show you that okay, for the example of the interface turbomachinery CFD, TCFD. And if there is something what I have missed or which is probably not correct set, I get an information here, and the information here, for instance, is that for that particular interface, I should not have special characters in the names. So this is quickly sorted out. So just rename that to, well, stator, that to impeller, and that just to volute. Okay, and now I'm able to export those data for all the components that were selected. Before that, I can set some parameters, which are basically triangulation parameters, where you set a minimum and a maximum element length, and where you set the granularity for the STL files to be exported. I'm going to leave that to default. Just press OK, and then it's going to take a couple of seconds for both the definition of the control file .tcfd, which is used then by TCFD and which holds all the information for the setup of the simulation runs, plus the STL files that cover all the solids that eventually build up the fluid space. So that takes probably a couple of seconds, but once that is finished, I can give that to TCFD, and TCFD could then start, after a couple of clicks, the simulation. Okay, so that's ready now. It tells me export was completed successfully, and maybe I can just use the remaining time to show you an additional feature, and it's probably easier to show it with the stator. There's a second tab in the meridional contour design step, which is called Hub Shroud Solids, and here you can, at the shroud, add a certain thickness. You can't do that at the hub at the moment because it's just a pipe where the hub radius is 0, and I can again right-click on the shroud and add a certain initial offset. So, for instance, 2 millimeters, and I can again click on the contour of that shroud line and can do a lot of alterations. Just insert Bezier points, make a split, join the curves, and so on. And by doing so, I can just define a real solid of the non-fluid space of my design. And if I press OK, you see it here also. But of course, if I just want to analyze the hydraulic behavior of the stage that was just designed, then this is not necessary. But of course, that needs to be done if you want to readily design the complete stage. Okay, and by saying that, I'm ready, and now I would like to make Radek to the presenter. Thank you so far.
Okay, so thank you, Oliver, for the CFturbo part. So now the centrifugal pump was created, and now it's time to switch to turbomachinery CFD to analyze that. So I'm gonna switch the presentation back to me. And yeah, so please let me give a brief description of what turbomachinery CFD is. So turbomachinery CFD is a unique software developed by Czech company CFD Support. It's a smart, easy to use, and affordable CFD software. Turbomachinery CFD was designed for CFD simulations of all standard rotating machinery, such as fans, pumps, compressors, turbines, turbochargers, hydroturbines, etc. Both axial and radial machines, both compressible and incompressible fluid flows. It's based on OpenFOAM CFD tool, and we believe turbomachinery CFD is unique, at least for 4 reasons. So So number one would be TurboMachinery CFD has no licensing, so which means our clients can keep TurboMachinery CFD forever and they can use it for unlimited number of users, jobs, or cores. What is paid for is the first delivery and technical support and software maintenance. Number two would be TurboMachinery CFD is fully automated, which means the workflow from the initial data to the final engineering results. It can be run by a single click or by a single command, and all the process is being done automatically. And for this reason, TurboMachinery CFD is extremely effective. Number three would be we deliver very good technical support. We are proud of it. We keep custom approach to every customer, to every issue, and we never leave behind any of our clients. So we are very flexible in it, and technical support is unlimited. So we support our clients even in matters out of the turbomachinery field, for example, in numerical mathematics, physics, CFD, or IT, or even software engineering. And the last one would be the real tutorials are included in TurboMachinery CFD, so the user has no doubts about the best practice settings that are included in the real machines that are preset. So basically, it's very easy to start with TurboMachinery CFD. So that's just a brief introduction. I will now switch to Radek. So Radek, are you ready for your live example of TurboMachinery CFD?
Yeah, Luboš, I am ready. So can you give
yes,
the presentation?
A pleasure. Yeah.
Okay, thank you. So I hope you see my screen, all of you. So thank you, Luboš, again, and also thank you to Oliver for designing and exporting the pump geometry for me, because now my task is very easy. And in this part of today's webinar, I'm going to show you how clever the TCFD is and how easy in general is to run CFD simulation using the CFturbo export or using the CFturbo interface. So today I'm using the brand new version of TCFD, which is the version 17.10.10, and therefore I will emphasize some new features of TCFD which have been implemented within the last version of TCFD. So to start working with TCFD and together with the with CFturbo export, I just need to find the export from Oliver. So I'm using NA file browser. So I have saved the CFturbo export in my working directory. So at the beginning, you have the exported geometry in STL files, which by clicking I can load in ParaView, which I have done before. So this is basically the input geometry for our TCFD. So every part of the geometry is exported in a separate STL file, which is the best way to work, which is the best input for our TCFD software. And at the same time, the CFturbo exports the control file or the configuration file for the TCFD run, TCFD simulation, to run it in an automatic way. Basically, it contains compulsory parameters which sets the CFD simulation, starting from defining the input geometry through defining the simulation parameter and ending with the post-processing setup. So this is the configuration file, and now start working with TCFD is really simple. I just need to double-click the configuration file, and the TCFD graphical user interface appear automatically. It was implemented directly within ParaView, which is a really nice tool for data visualization. And as you can see in the left menu, or in the left box, there is a menu using which you can set all parameters which are important for CFD simulation. So now I have no job to do, because everything is set automatically, and export it automatically from CFturbo. So I will just, in a few clicks, I will show you how to run the simulation, and then I will explain some parts of the setup in more details. So basically, at the beginning, only what you need to check is to go to the simulation item, and here is the number of processors. So now I just need to change this number of processor for my particular machine. So now I am on the laptop, which has only 4 cores. So I will set it to 2 to have another computational effort for post-processing, for example. So I just need to change the number of processor, and I click, because everything is automatically set, so my geometry is automatically loaded and visualized in this render view. And because everything is automatically set up, so now I just need to click on this radial pump or setting item in this pipeline browser, and then I am able to apply the TCFD manager, which is the manager which manages the simulation, the CFD simulation. So at the beginning, I just need to define my directory name in which whole simulation will be stored. So for example, webinar simulation. Then I click to apply to approve my name. Then I just click to write the case. So it writes every compulsory and important directory structure and files before we can run the simulation. And after that, I just need to click run all, and everything will be run. So basically the mesh will be created, the simulation will be run, and the automatic post-processing features will be evaluated. Or I have also option to first to generate each component of my machine, or I can first mesh all, look at the mesh, and then run the calculation. So I will just click run all, and this TCFD manager make all steps of CFD workflow automatically. So in the meanwhile, I can go back to the setting part and just quickly introduce the item in this menu. So first one is just to tell which configuration file to use, or if you start from scratch, you just define the file in which you will store the setup which you make here. In the simulation, you define the processor number. There is no limitation to the amount of the processor, so you can use any number without any restriction. The numerical order, you can choose between first and second. You can choose steady state or transient simulation. What I missed or what I forget, just to emphasize that our software provides many types of machines. So in this case, pump, or it also provides turbine, water turbine, fan, and compressors. So now we are working with pump geometry. Inside the components part, you define, or the user defines the computational mesh using the STL file. So basically, you load the directory with the STL files, and then you set the type of each boundary. It is very straightforward. Basically, the inlet is inlet, the interfaces are interfaces. I mean the interfaces between the components, for example, between the inlet pipe, which is colored by white color, and between the wheel, which is colored in red color. Then you can play around with the mesh refinement. You can add layers at the wall, and you can set the communication between the interfaces. Basically, you can use arbitrary mesh interface or mixing plane approach, as is usual in, let's say, commercial softwares. This is done for each component. If you're starting from scratch, here is a nice graph, the topology graph of your geometry. So usually it shows you which part is connected to which part, what is the physical inlet, and what is the physical outlet. So it's a really nice tool, mainly if you are starting from scratch. Okay, other parts are speed lines. So you can, for example, set several speed lines to be simulated. It's not usually for pumps, but for example, for turbines or compressors, you can simulate more speed lines within the one simulation or within the one computation. So you set the velocity or the rotation speed in rotation per minute or in radians in seconds. Then for each speed line, that is for each rotation speed, you can define several points to be simulated. Basically, each point holds different boundary conditions, so different condition of your simulation, usually different pressure drops in your machines, and so on. Then you can set the turbulence model, K omega, CST, K epsilon, and others. Here you set the boundary and inlet and outlet boundary condition. You can set the mass flow, or you can set the pressure drop. Initial conditions, so how to initialize the first simulation. Simulation control, some advanced parameter, such like a relaxation or bounding values to make the solver more robust. What is really nice is the post-processing item, in which you can set an automatic post-processing. For example, the averaging window means the size of the window in which all variables are averaged, to see really the average value at the end. What is the new feature? Now you can work with non-SI units, so you can set the pressure in bars, in atmospheric pressure, PSI, and other dimensions. The same holds for other variables. Efficiency pros is nice, so usually CFD likes long inlets and outlets, but for example, you have the measurement really before the wheel and after the volute, so you can define it really here, which places are used for the efficiency, pressure drop, and other parameters evaluation. Blade-to-blade view, there's automatically set blade-to-blade view and the visualization of the given field, for example, relative velocity at some radial span surface, which is also automatically evaluated, and also you can evaluate any variable at the meridional plane, and it visualizes the meridional averages. But what is also nice too, you can add additional data files to compare with your measurement, to compare with old simulation or with other simulation. So automatically you can add, and these graphs will appear directly in the report. In this menu, they are set up for the meshing application, and you can add the scripting. So basically, this Python script, using which you can utilize, or you can define your own post-processing tools, your own turbulence model, let's say, and many other things. Okay, so this was a quick introduction to this menu. What I missed, and it is really important inside the physics, you can set basically the fluid parameters. So there are the default is, or there are preset values for the water or air, but in this case we have the pump, so the water is sensible choice. For compressible cases, which is not this case, you can enable compressible solver. Here are the parameters, and also you can enable the cavitation risk. And moreover, if you set the transient simulation, so basically steady state plus transient means that the transient simulation is initialized by the results of the steady state. And if you enable this transient solver, now you can enable the multi-phase cavitation, which is the full multi-phase cavitation solver, which gives you really detailed information about the cavitation in your geometry. And it uses so-called Schner's-Sauer cavitation model, and here are the parameters of this model. Yeah, so this can be also simulated within the TCFD. So I will push it back to the steady state. And what I would like to say at the end, yes. Also, the new features is that you can add the rough walls. So after that, the wall function, which can model the rough walls in your geometry, is applied. So it can be enabled here. And the last thing is the initial condition. And here you have option to set the manual initialization using the default value on the velocity and pressure in the whole domain, or you can use the mapped, and basically you load the previous, let's say, some previous computation on this geometry, which will be used for the initialization, which can really speed up the convergence process. So I have no available data now, so I will use the manual. Okay, and in this case, you can really change the parameters, and afterwards you will done it. You click on apply to approve them, and inside the TCFD manager, you will write the case and run the simulation. So as you see, my machine process is still in progress, and at the end, so I will make a time jump, which I have here. Okay, yes. So this is the state at the end of the meshing process. What I can do, for example, I would like to see really my mesh, so I can click on the show menu here, click on apply. So now the given component is automatically loaded inside this graphical user interface, and I can visualize it here. Just to zoom out, I can see the topology of my mesh. I can apply any filter which is available in ParaView just to analyze my mesh and many other stuff. And after that, I can click on run calculation when my mesh is okay for me. And then I can watch really the progress of the simulation. So I am always informed which iteration is computed at the moment, the time, the end time of the simulation, and many other stuff. I can skip to the next point of the simulation. I can abort the calculation anytime I need. And also during the simulation, I can generate the report, so-called light report. So it generates basic information about the residuals of the solver, about the current efficiency and head values of my pump, and many other. And at the end, if I click on run all, so at the end the full report is automatically generated. Or if I really clicking step by step, so at the end of the simulation I can click to generate the full report manually. And if I done it, if I do this, so at the end, which I have prepared here, so as you can see, the simulation is done, the report is generated and automatically appear here in my right window. So I can go through my report directly here. I can also load the case by clicking on the show results, which I have done, and then you can really watch, for example, pressure distribution or any other variable which is available for the particular solver. So for example, relative velocity, cavitation risk. So basically it shows you the cells, so parts of parts of the computational domain in which the cavitation may occur, and many other. And you can open the case anytime you want after the simulation is done. So if I go here, for example, my radial palm, this is my computed case which I ran before the webinar, and inside here you find all information about the simulation. Anytime you can click on this case foam and the paraview for the visualization will appear automatically. Then you are able, for example, here you are able really to see the distribution of any variable. So you can visualize it. You can, for example, visualize the 3D streamlines throughout your geometry. You can, for example, just visualize the pressure contours at the wheel, at the rotor wheel, or you can apply this turbo unwrap filter and visualize really the unwrapped blade to see nicely the contours of the pressure, or you can even make the slices to see really the distribution of pressure, total pressure, velocity at the given radial coordinate between hub and the shroud. So there are thousands possibilities how to visualize your results. And what is the best way, or what is the best, is that, which I have here, that the automatic report in the HTML format is generated, and you can anytime open it. And it basically contains the most important parameters of your computation. So you can see your geometry at the beginning. You can read here the basic information about your simulation, like rotation speed, mesh size, so basically mesh size of each component, and the total amount of cells in the whole computational domain. You can look for Y+, which is important for turbulence modeling. You can see how does it take to simulate your machine, how long does it take, of course, fluid name and compressibility check, the residual control throughout the whole simulation, the flow rate, convergence, and then there are several parts dedicated to given variable. So first one is, for example, the head. So you can see the head distribution along your defined points. So basically here was defined several flow rates regime in the simulation, and you can also watch the convergence, and also here are tabulated values which can be nicely taken and post-processed afterwards. Another one is the efficiency, so which is important, so you can read the best efficiency point for your machine. And another new feature, if you can anytime click on any figure to zoom in and carefully read the values from this figure. For example, again, efficiency, convergence of the efficiency, the torque for each point of the simulation, total pressure difference, so total pressure difference between inlet and outlet, or between your predefined efficiency probes, total pressure per interfaces, so you can directly check on which interface you would like to visualize the pressure for your given point. So for example, you can visualize the values at the interface between the pipe and the impeller. You can visualize the interface between volute and impeller to see the pressure, total pressure with respect to the flow rate. And another nice graph, you can see the distribution of the pressure along your geometry, so from the inlet to the outlet. So really to see where is the pressure drop, where is the pressure lost, and so on. Another one is the magnitude per interfaces. To follow the velocity magnitude, again you can choose the interface. And the last, circumferential and meridional angle, just to see the angle of attack to your blade, or the angle of the outlet angle from the wheel to volute and other parts. And the last part is dedicated to the cavitation. So because I enabled the cavitation race, so I can see the cavitating volume and cavitating surface for each point, the convergence, and also the cavitation index, which is famous within the water pump and water turbine simulation. And also the new feature is that there is also included this net positive suction head, which is a parameter exclusively connected to the cavitation inside the water pumps and water turbines. Then automatical post-processing of blade-to-blade view. So now, for example, you can read the streamlines at the span 0.1. So it means it is radial slice at 10% from hub for each point, so you can compare that what is happening at the given condition of the simulation. And here the same for another span, which is directly in the middle between hub and shroud. The last one, and for example also the meridional average, so to see the meridional average at the meridional plane for the given variable. So here is the static pressure distribution, for example, at the wheel. And the second one, we define the total pressure, or no, this is the, this is axial, radial, coordinate, velocity, magnitude of only the axial and radial component of the velocity. Okay, so my time is up, so I have to hand back the presentation to Luboš. So Luboš, are you ready? Are you online?
Yes, of course. So thank you, Radek, for your live demonstration of the CFD simulation of the pump, which was created by Oliver in the previous section. And let's move ahead. So I'll take back the presentation. So this was the live example of the simulation. And here we go. It's time for your questions and our answers. So I'll take a look what we have, and I can see we have a number of questions. So I suggest some are addressed, of course, to CFturbo. The other group is addressed to Russian CFD. So I suggest to go by the programs, by the groups. So Oliver, may I give you all the questions on the CFturbo?
Sure, you can.
Okay, so I'll try to pick the right one. So the first one, is it possible to generate the double suction impeller meant in CFturbo?
Right now, it's not possible. It's on our list, but the demand by customers is not so high right now that that it has not top priority. But of course, it's on our to-do list.
Okay. Another one. Can CFturbo be used with a software like iSight for DOE and optimization?
Yes, it can, because as I said, everything is parameterized, and also CFturbo can be run on a command line, which means you can put it into a batch process and can use, for instance, an optimization package that controls all the changes in CFturbo, and then the proper exports will be done, and those exports again can be used in any simulation packages. And that has been done for a couple of optimization packages. and some of the customers use it, and we have developed some workflows that have been also published on conferences and so on.
Okay, thanks. So the next question is, at CFturbo, can we bring our test data to improve upon or extend the built-in empirical models? So the question. Yep.
Yes, as I showed, we have these approximation functions that we call so, and they are just can be extended by any parameters. Yes. Oh, thanks. Right. If I, for instance, go back to the impeller and to the main dimensions, we have these parameters like the work coefficient that I already showed, and the data that are used in the design process are saved in our approximation function, and a customer can at any time add his own data here. So for instance, test, of course, and then copy and paste data points from, for instance, an Excel sheet, put them in here, and can save that in a file which is called CFD-FU, which is an XML file, and that file will be saved on the desktop of this customer and can then be used in the design process. So the knowledge will stay in the company and will not make public to anybody else, including ourselves.
Okay, thanks. The next question is it possible to take a trial version of CFturbo?
It is. One has to apply for that. We usually give test licenses for a period of 3 to 4 weeks, and we give that to companies and universities. And if there is somebody from a university who wants to test it, then there should be a professor in charge of that, and he then should apply for that test license.
Okay. The next question: have you made any comparison of your built-in mainline code with some other codes like CenCom or CompAero? Yeah.
No, we haven't, because there are other ways to validate the code, and other, not only other, but also better ways. One way would, for instance, be checking the design with the help of CFD, which has been done a lot because we also do a lot of projects for customers. And the very best validation process is if you have satisfied customers. And we are on the market for a couple of years now, and we can say that they are, in most of the cases, very happy with the software.
Okay. Can CFturbo can you design return channels for multi-scale compressors?
Yes, return channels can be designed. So I can quickly show an example, which is
yes, sure.
not a compressor, but well, no, I even can show a two-stage compressor that maybe just will show how a return channel would look like.
Okay.
1 second.
Yeah.
Okay, here it is, and we have 2 stages, and you see here that's the first impeller with splitter blades, and on the back of that there is that return channel that has also some vanes. So yes, that's possible.
Okay, thanks. Yeah, the next question would be, in CFturbo, can you control the blade and meridional curvature distribution directly?
No, you can only just watch how, if I go, for instance, to that, how any change, so we have the curvature progression here, how any change of the volute will result in a certain curvature distribution. But you cannot do the vice versa way. So setting up a curvature and then get a meridional shape, but very quickly you get an answer at after any change of any of the control points.
Yes, right. And the next question, in CFturbo, are the blade defined flank millable? I don't know what it
Yes, because it's good that I have opened that example, because when you go to the blade set property design step, you can change you can choose from a different sets of blade shapes, and one set is what is called ruled surface, and once you have chosen that, then you can flank mill the impeller, and that's very often applied for compressors.
Okay. Do we have any comparison of CFturbo prediction to CFD results?
Well, the prediction is based on very simple models. That's why we do not recommend to make use of it. It gives you only a very rough estimate of what you get. So that's why we don't have put a lot of effort on tweak that model, tweak with the help of CFD or measurements also, and that's why I would not recommend to use it, and also it's not widely validated against any measurements or so.
Okay, yeah. The next question is, in CFturbo, are the hub shroud and blade-to-blade loading at the hub and shroud streamlines plotted?
Oh yes. When I go again to the mean line design step, there are these models implemented to quickly calculate the relative velocity and the induced velocities at leading at pressure and suction side, and from those definitions one can also calculate the blade loading, and one gets that for the mid span, for the hub span, and for the shroud span.
Okay, and for now, the last question for on CFturbo is there any way of fixing the points coordinates during the meridional contour design?
To fix the points coordinates, oh, maybe I don't understand it thoroughly, but yeah. Once the points are set, just by right-click and typing in some data, then they are fixed. There will be a change of the points once one, for instance, changes the impeller diameter in the design step before. But this is necessary because otherwise, for instance, those trailing edge control points would still remain at the same position, whereas the impeller diameter is higher. So yeah, there is always a certain parametric relation between control points and diameters and stuff like that. Yeah, so it's not easy to answer this question thoroughly. I think it depends on the special case.
Yes, of course. It's yeah. Okay, so it seems the questions are on CFturbo are over. So now let's go quickly through questions on Turbo Machinery CFD. So is it possible to make a hex mesh with boundary layer, Radek?
Okay, so if you mean the fully structured or block structured hex mesh, it's not. We are not able to do that with Snappy Hex Mesh tool, which we are using. It creates the dominant hexahedral mesh, but let's say, it changes the shape of the hexas like tetrahedras, and so in the neighborhood of the surfaces. But there is option to add layers. Well, where's my components? You can quickly set, for example, at the pipe wall, I can set 3 layers, and then inside the menu, meshing option, then I can enable for each component. Here, add layers, and here you prescribe the layer sizes. So it can be done to add layers here, but it's not structured or block structured hexahedral mesh here. But anyway, it can be exported from any external meshing tool. Here using, so you can geometry source. There is more option, not only the STL files, but also the external OpenFOAM mesh. It means there are a lot of transformation. You can export and you can convert, for example, the Fluent mesh or any other mesh, Mecha mesh to the OpenFOAM and load it directly here.
Okay, so next question. Input is usually only speed and outlet restriction, others are calculated. Do you have any example of showing that?
Well, so here are the inlet and outlet condition. So in this case, we prescribe the volumetric flow rate, but you can also describe the directed mass flow rate or volumetric, so you can also prescribe the direction and the total pressure at the inlet, and at the outlet, of course, there is usually the static pressure, fixed pressure, and the outlet or outlet vent, which is more dedicated to compressor case. So there are options using the volumetric flow rate, which corresponds to the velocity, right? If you know the surface of the inlet, and or the total pressure at the inlet.
Okay. The next question is, for a speed line, can we define different types of boundary conditions for each speed line?
It is not available now. So for speed line, you have only option to choose all inlet condition as volumetric or mass flow rate or velocity flow rate. But you can, for example, quickly you can define 2 speed lines with the same speed, and first half simulated with volumetric flow rate, and the second half simulated with total pressure.
Okay, so it's,
for example.
Okay. Is it possible to make the hex mesh? Yeah, I answer directly. No, it's
no. Yeah. The structured block structured hex mesh is it's not can be done within TCFD, but can be imported from external meshing tool easily.
Yeah. Okay. Can we see the results live during the simulation?
Oh yes, we can see the average values at the interfaces. So what I have done, for example, so this is my running case. I click on the light report, and I can see online, for example, the residuals. I can see online the head convergence process. I can see online the efficiency, and yeah, that is all in the light report. But I can also generate the full report, and the values which are available will be visualized within the report. Or moreover, you can go directly into the case, which is my here is my webinar simulation, and inside the log run there are all outputs from the simulation, or inside the post-processing there is the efficiency file, in which, so there is CSV file. If I open it, I will maybe it's too large. Oh yeah, no, something is happening. So here you have all values for all iteration implemented here. So for example, in each iteration you can follow the efficiency, average efficiency, I don't know, the top pressure at the inlet. So every value can be follow runtime, both within graphical user interface or directly in the given file. In the case.
Okay, thank you, Radek. So I see we are running badly over time, so I think we should conclude here. So I'm gonna conclude. So Yes, so this was the Q&A session, and I think we are. I think this is it from us in this webinar. I think it's time to finish. So feel free to contact us. I'm sure you know very well how to do that. The questions about CFturbo are to be sent to CFturbo company. The questions on Turbo Machinery CFD are to be sent to the CFD support, and we will gladly support you in your Turbo Machinery projects. It's our job and also a pleasure for us. So feel free to put your questions, and we will gladly answer all of them. Yeah, anything more to say, Oliver?
I just want to say thank you to all the audience for your time, and I hope we can get in touch somehow. Thank you. Bye-bye.
Okay, thank you, Oliver and Radek.
Also, I would like to thank you all attendees to watching us, and we are really looking forward for your questions or for your contact with us, and also hoping to stay in touch in the future.
All right, so yeah, thank you for your attention. We are looking forward to collaborating with you, and stay tuned, and bye-bye for now. Bye.